Hello everyone, welcome to Statistical Methods. With this video we will be starting part 2 of the module about Bayesian statistics. So in this video I will be giving a brief introduction over the principles of Bayesian learning. If you like to read this yourself, then go to the lecture notes in chapter 7 and then you can find everything we are discussing today. So let's start straight into Bayes statistics. So topic is, what is Bayesian statistics and what is Bayesian learning? So first of all, this goes back to Thomas Bayes, and he lived in the 1600s and 16th century, sorry, and so he was born at the beginning of the 16th century, and then he died 60 years later. And Bayesian statistics is actually based on a theorem published in a paper that was published after his death, based on his work. So Bayes' theorem was published 1763, and it was actually published by his friend and colleague Price. I think William Price, but definitely Price. So what is this Bayes' theorem? Basically it's a theorem about conditional probabilities. So we can write the conditional probability of A given B times probability of B is the same as the probability of B given A times probability of A, and if you divide by the probability of B you get Bayes' theorem, which is that the probability of A given B is, so this is A. So probability of A given B is the probability of B given A times the probability of A divided by probability of B. So what this allows us is to reverse the conditioning. So note different order of the arguments. So this of course is a probability theorem. So it's probability theory. It has nothing to do with statistics. So just a theorem about conditional probability. So this is valid because it's a mathematical fact from probability theory. So where does the statistics come in? Statistics, as we discussed, is about characterizing uncertainties. So the Bayesian learning principle uses Bayes' theorem to update information about the uncertainty of an event. So Bayesian learning update our uncertainty about an event And events is very broadly defined, and can of course also be that the event that a parameter takes a certain value. So that's also an event. But of course also the event that it's snowing tomorrow, that's also an event. So what we usually have is we have this, let's say, theta. If we talk about parameters, theta is a parameter, and that's unknown true value. Then we have a distribution. That's the prior distribution. So that's something that's new in Bayesian statistics. So we have a prior distribution. And this prior distribution describes our knowledge, our current knowledge current state of knowledge, describing the uncertainty about theta. So the key thing is we're not interested in the randomness of theta, because theta isn't random. Theta is a parameter that is unknown, and we have a state of knowledge that we use a prior distribution to describe the state of knowledge. But so we use the mechanism of a random variable to describe uncertainty. So then we have a data generating process. And this data generating process is of course given by our model. Probability of x given theta, that's basically the likelihood if x is all the data. So what's the principle of Bayesian learning? That is simply use Bayes' theorem to update our state of knowledge. So this is done as follows. So we compute the probability of theta given x from Bayes' theorem, and that is basically the prior times the probability of x given theta divided by the probability of x. So what you can see here, so we have a posterior distribution. This posterior distribution describes our uncertainty about theta after taking into account data x. And this is of course the likelihood and this is the prior, and this here is basically the probability of the data, the unconditioned probability where we have marginalized out the model and all the parameters. And this thing here is actually difficult to compute, so this part, and that's why Bayesian statistics hasn't really taken off until, I would say, 1990 roughly, because you need a lot of computing power to compute the probability of X. So let's draw this visually. So what usually happens is as follows. So we have prior, and this is our theta, and usually it's kind of broad, and then we have data, and suddenly after seeing the data we get a posterior and we learn something, and suddenly it will be like this. So that's theta. So that's a typical scenario. So after seeing, we have basically, before we have a vague idea about theta, and later after seeing the data we have a more concrete idea about theta. So that's theta given X. Okay, I mentioned the probability of X, and that's computed as the marginalization. So we have the expectation over X, so we need a distribution over the theta, and that's our prior distribution. So this is an integral of times the probability of theta d theta, and because this is the prior, this is sometimes called prior predictive distribution, because it tells us under the prior what's the probability to observe X. So that's a prior for X, and sometimes it's also called simply just marginal likelihood, because we marginalize the theta out of it. But of course, I think personally marginal likelihood is a little bit, it's a marginalized likelihood, but given, because there's no parameter left, actually it's not a function of a parameter. So, and this needs to be computed for computing the so we needs to be computed for the posterior probability. So, and that's, as I said before, this can be quite tricky. But a key thing, what's interesting is here, and that's something that's already pointing towards a key difference. So the key difference to maximum likelihood is, in maximum likelihood we optimize. So in ML we optimize, so we find a maximum. In Bayes we tend to average out using a prior distribution, or you can also average over the posterior distribution, then it would be called posterior predictive distribution. So it's two different principles, averaging versus optimizing. So that's how the Bayesian learning procedure works. You have some information, you get data, and then you update your information using Bayes' theorem. So often, of course, we would like to compare Bayesian statistics with other statistical methods, and then we need to ask ourselves, what do we call the Bayesian estimate? So what's a Bayes estimate? What's this? So the Bayes estimate is the full posterior distribution. So nothing less, but nothing more. And often we need to compare with point estimates or with interval estimates. So we can basically extract point estimate and interval estimates from the posterior. So typical point estimates would be posterior mean. So we take the mean distribution, so it would be the expectation of theta given x, or we take the posterior variance, and so then we can have the posterior mode, and the interval estimate would be construct credible regions or credible interval by reading off quantiles from posterior. So we just take this posterior distribution, and then we say 95 credible interval. So it's called credible interval, not confidence interval in Bayes, when we have 95% of the probability in this. So 95% probability. And then in this case we can actually talk about the probability that true value is in interval. So this is actually the natural interpretation of credible intervals. And so we can construct two-sided intervals the usual way, and we can also construct so-called highest posterior density intervals by trying to make the support as short as possible. So we can have two-sided intervals, and we can have compact intervals. And they're called HTP, credible intervals. Okay, so this is basically the estimate. So, but you need to get the posterior distribution first, and then from the posterior distribution you can read off point estimates, mode, mean, variance, and you can read off confidence intervals. No, I'm saying it the wrong way. Credible intervals, and you can choose the credible intervals to have you can move the, if you want to have a 95% credible interval, then you just need to define whether you want a two-sided interval, for instance, or you want a compact interval, and if the posterior is not symmetric, then those are different. So let's look into how to do this on the computer. As I said before, computing the posterior probability density is actually quite complicated. So what you normally need to do is you do some sampling from the posterior, and there are techniques like Markov chain Monte Carlo or MCMC that are widely used in Bayesian statistics, and you need to do integration, high-dimensional integration typically. So it's all non-trivial things. So to make things easier, there have been a lot of work in the area of Bayesian statistics and implementation in computer languages, and for instance you can do it in R using something called STAN. So STAN is a probabilistic programming language. Specially designed, so STAN, S-T-A-N. And there are others, like if you work in Python, probably the most widely package to do Bayesian learning is PyYNC3, and it has it in the name already, so you have Python and then Monte Carlo, and 3 is just the version number. So this would be your package of choice in Python. And there are a few others, and I'll put some links in the lecture notes. So these were just the introduction. So we have a computer program to do the inference. We update the prior to the posterior, and so technically it's all relatively straightforward, and it becomes more complicated when we actually look into the individual models, which we also will do soon. So let's now discuss the difference between frequentist and Bayesian statistics. So differences, because when you're Bayesian, then not nowadays, but there used to be a need to defend yourself why you're doing it in a Bayesian way. And clearly, so from our perspective now, there are some very strong arguments why one needs to use Bayesian statistics. And one particular argument is that the large sample optimality of maximum likelihood is not valid for small samples. So for small samples you need to do something else, and this something else is actually methods that link with the Bayesian framework. So, but before we discuss this, we talk about differences of so the classical statistics and Bayesian statistics, and these are to some extent philosophical differences. So first of all, using Bayes' theorem doesn't really using Bayes' theorem is not the same as Bayesian statistics. So using Bayes' theorem to update your uncertainty is Bayesian statistics, but using Bayes' theorem just in any arbitrary context is just using Bayes' theorem. So using Bayes' theorem does not make you Bayesian. It's just a mathematical theorem. That's true. So what makes you Bayesian is actually how we interpret probability. So there are different ways how to interpret probability. And on the one hand, we have a frequentist interpretation. And the frequentist interpretation is basically probability as limit of a frequency. So that's why it's called frequentist. And this is a view that is often taken in probability theory, because of course of the law of large numbers and other limit theorems. You can see that when we have a frequency and we have infinitely many repeats of these experiments, then we have a frequency that converges to the probability, and that's actually true. So that's called the ontological view, because frequency is something that exists. So then we have the Bayesian view of probability, and that is probability is a state of knowledge. Is state of knowledge and is used to characterize the uncertainty, and most importantly, we can update the uncertainty by data. Update uncertainty, so the probabilities can change. And this view is called the epistemological view. So that's, there have been some famous statisticians that actually, in particular Definetti, and he was saying that Bayesian probability doesn't exist, and he meant that it's not ontological. So probability doesn't exist, probability is assigned. And it can change. So it's a epistemological property. And I would say most statisticians today take this view that we use statistics to characterize our uncertainty, and we update our uncertainty using Bayes' theorem or other methods. It's not the only way to update our uncertainty. And if we take this stance of probability, then you are actually a Bayesian statistician. So that's for the background. In the script you'll find an overview over some historical developments that I won't recap here. So I started script. You can find more about the history. You can read about this. So basically it started off with Bayesian, and then the frequentist took over, and now it's actually the tide is turning. Now basically everyone is a Bayesian, or many people are Bayesian again. So One last thing that is important and that I also would like to mention. So Bayesian learning. So we started off in this course with entropy learning. And we saw that entropy gives rise to maximum likelihood. And it's actually, intriguingly, it's also the case that entropy also allows to derive Bayes' theorem. And this is interesting because basically there's a principle called entropy learning. So like Bayesian learning, it's an update rule, and is from Kullback from 1959, and it's basically the principle of minimum information update. So that's this entropy learning thing. So this is Kullback, and it says that you have your assumptions or your characterization of uncertainty about something, and then there's new information that arrives, and often it arrives in form of observations and new data. And then we only change the model in such a way, or not the model, our uncertainty about the parameter or event in such a way that it's minimally changed. And this minimal change is of course measured by the Kullback-Leibler divergence. And under this principle of minimum information update, we can actually get back Bayes' theorem. So Bayes' theorem fulfills exactly this principle of minimum information update. So you have information that derives as data, and then the Kullback-Leibler divergence between actually the posterior and the posterior and the prior is minimized, because you only want to change your prior as much as needed. So change Bayes' theorem changes prior only as much as is necessary. So, and it's the optimal way to learn. If information arrives in form of data. If the information doesn't arrive in the form of data, but for instance in the form of constraints, then we can actually just directly use entropy criterion. That's it for today. So you find this and also a few other things in the chapter 7 in the lecture notes, and in the next video I will explain how to apply this in practice to a concrete example, namely the example of how to estimate a proportion. Until then, so see you in the next video. Bye bye.